Hey, what's up, chem peeps? Who's ready for some intermolecular forces practice? In this vid, we're going to focus on the intermolecular forces that occur between organic molecules. You will recognize that these organic molecules are carbon-based compounds. And if it's strictly carbon and hydrogen in the compound, we call them hydrocarbons. And perhaps most importantly, the carbon and hydrogen are close enough in electronegativity that the covalent bond that forms between them is considered nonpolar. Alright, let's take a look at some examples. Examine the Lewis structures for the organic molecules and indicate the type of intermolecular forces present. In this first example, we've got a couple of benzene rings. Great example of a cyclic hydrocarbon made up of just carbon and hydrogen atoms. So when it's just carbon and hydrogen, the bonds are considered nonpolar, and therefore we don't have any strong type of dipole-dipole interaction. However, because benzene rings have electrons, we will have London dispersion forces. Boom. And that is the only type of intermolecular force that we're going to see between two molecules of benzene. Alright, now let's take a look at a molecule of adenine and thymine. Two of the bases in DNA. Oh, throwback to biology. So again, these are organic molecules, but it's a little more complex when we think about the intermolecular forces present between these two molecules, because it's not strictly carbon and hydrogen. Still a lot of carbon and hydrogen, but as you notice, we've got some nitrogen and some oxygen in there. Let's start with adenine. Notice here that we have a nitrogen covalently bound to a hydrogen. Because nitrogen is so much more electronegative, this bond creates a fairly strong dipole moment. It's pretty polar. That's true here as well, and also on the thymine molecule. In addition, on the adenine molecule, the nitrogen in part of this ring here is more electronegative than the carbon here or here. And although not drawn in, there's a lone pair of electrons on this molecule. Remember, the nitrogen strictly follows the octet rule. Why is that important? We've got a dipole here as well. Slightly negative region by the nitrogen. On the thymine molecule, a similar thing is going to occur, but this time it's going to be between the oxygen and the carbon that it's bonded to. It's going to create a dipole moment, or a slightly negative and slightly positive region because of those differences in electronegativity. Same thing here. Alright, now let's try to identify the types of intermolecular forces that exist between these two molecules. Well, there are electrons involved here, so anytime you've got electrons involved, you know we've got to have London dispersion forces. Boom. But we're also going to have some dipole-dipole interaction. The negative region on the thymine molecule here is going to interact with the positive region on the adenine molecule over here. Dipole-dipole interaction. We also see that dipole-dipole interaction between the negative region on the adenine molecule here and the positive region on the thymine molecule here. Dipole-dipole. And then finally, recognize that this type of dipole-dipole interaction is the strong type. We've got hydrogen covalently bound to one of those fun elements, nitrogen. It's really pulling away those electrons in that covalent bond, exposing the positive proton in hydrogen. Meaning that the attraction between adenine and thymine is a really strong dipole-dipole interaction. We call it hydrogen bonding. So that might be a throwback to the good old days of biology as you talked about those DNA base pairs. How are they connected? A hydrogen bond. Moving right along. As you take a look at these two molecules, let's first identify that they've got electrons. So we're going to see some London dispersion forces acting in between the molecules. Boom. Next, let's identify where we might find some dipoles in these molecules. I'm going to focus here on the very electronegative oxygen. It's going to create a dipole moment due to the polar nature of the bond between hydrogen and oxygen. It's so electronegative, it's also going to pull the electrons in the bond between carbon and oxygen. These are two identical molecules, and we'll see the same thing happen on this molecule over here. Now, it might be a little difficult to see based on how they're oriented, but notice that when I turn this molecule a little bit, the positive end of this molecule could interact with the negative region of this molecule. So we've got some dipole-dipole interactions. And then finally, ask yourself, is it the strong type of dipole-dipole interaction? You bet, because this hydrogen is covalently bound to oxygen, one of the fun elements. So we've also got some hydrogen bonding. And remember, we often depict that using a dashed line because it is such a strong intermolecular force. Alright, that brings us to our final example for this video. We got a couple of molecules of octane. Now these look like pretty intense organic molecules. And they are, no hate to the octane. But the only types of interactions that we're going to see between two molecules of octane is London dispersion forces. These are straight up hydrocarbons. And remember, the carbon-hydrogen bond is not considered polar. Now, we're going to have some pretty strong London dispersion forces because we've got a lot of electrons there, but that's our only classification of intermolecular forces that we'll see between two molecules of octane. And we are done.